Hello guys and welcome to the next tutorial of ethical hacking and penetration testing via Kali Linux, and we are learning cryptography in this tutorial. So in the previous tutorial I taught you about what exactly cryptography is and how it works. So there are basically two ways to make a strong cipher, that is the stream cipher and the block cipher. So in the former you can make encryption rule, that in the former I mean the stream cipher, you can make the encryption rule depend on plain text symbol, and that is you can go ahead and position in the stream of plain text symbols, while in block cipher you have to encrypt several plain text symbols at once in a block. So to make it more precise or more clearer, this is an example that I would be showing you. This is how people used to go ahead and send messages in the previous days. So this was the plain text cipher, and this was the key when it was decrypted. This was the exact cipher that came out when it was encrypted. Again, when this key was used, you can see that the key is different. When this key was used, the plain text was exactly the opposite. That's Hail Hitler, and it was here Hang Hitler. But this is what the original the message was. This was the spy's what he told the message would be, but this was manipulated because he used two different things, the key from over here and cipher from over here, but the plain text was from over here. This is how you could go ahead and manipulate different types of ciphertext. The one-time pad is still used for high-level diplomatic and intelligence traffic, but it consumes as much key material as there is traffic. Hence it is too expensive for most applications, and it's more common for mainstream, or you can say as stream ciphers, to use a suitable pseudo-random number generator to expand a short key into a long key stream. The data is, you can say, it's not encrypted. It's encrypted but not that hard, but it's encrypted by using the exclusive O-ring in the key stream, one bit at a time along with the data. It's not enough for the key stream to appear random in the sense of, let's say, passing the standard series randomness test. It also must have the property that an opponent who gets their hands on even a number of keystream bits should not be able to predict any more of them. That means even if they have half the knowledge of exactly what is happening, they should not have the remaining knowledge just with the half of the knowledge. So you need to formalize this more tightly in the next section. Stream ciphers are commonly used nowadays in hardware applications where the number of gates has to be minimized to save power. I will look at some actual designs in later tutorials, including the A5 algorithm used to encipher GSM mobile traffic, and the multiplex shift register system that's used in pay-per-view TV or copyright and privacy protection, or you can see, like, for example, the Kaspersky key, for example, where you are only allowed to go ahead and use the antivirus if you have a corporation for only selected computers. For more, you need to go ahead and purchase or buy more of their stuff. So, however, block ciphers are more suited for many applications where encryption is done in software. So let's look at some of them. The random oracle. So before delving into the detailed design of modern ciphers, I want to take a few pages to refine the definitions of the various types of cipher. So readers who are the people who are watching, who are phobic about theoretical computer science, can go ahead and skip this section, but I included this because it was you need a basic understanding of random oracles before you go ahead and proceed further, before you go ahead and understand many recent research papers on cryptography. The oracle model, or the random oracle model, seeks to formalize the idea that a cipher is good if and when viewed in a suitable way. It is distinguishable from a random function of a certain type. I will call a cryptographic primitive pseudo-random if it passes all the statistical and other tests that a random function of the appropriate type would pass. In whichever model of computation we are using, of course the cryptographic primitive will actually be an algorithm implemented as an array of gates in hardware or a program in software, but the outputs should look random by being indistinguishable from a suitable random oracle given the type and the number of text that our computation model permits. In this way, we can hope to, let's say, separate the problem of designing ciphers from the problem of using them correctly. Mathematicians who design ciphers can provide evidence that the cipher is pseudo-random. Quite separately, a computer scientist who has designed a cryptographic protocol can try to prove that it is secure on the assumption that the crypto primitives used to implement it are pseudo-random. The process is not infallible because, as I saw with proof of protocol correctness, theorems can have bugs similar to programs. Programs could be idealized wrongly, or the mathematicians might be using a different model of computation from the computer scientist. But at least some progress can be made though. So you can visualize a random oracle as an elf sitting in a black box, as you can see in the lower part of this image, and with a source of physical randomness and some means of storage. So the elf will accept inputs of certain type, then look in the scroll to see whether this query has ever been answered before. If so, it will give the answer it finds. If not, it will generate an answer at random times by throwing the dice. I'll further assume that there is some kind of bandwidth limitation, that the elf will answer only so many queries every second. This ideal will turn out to be useful as a way of refining our notions of a stream cipher, a hash function, a block cipher, a public key encryption algorithm, and a digital signature screen. Finally, we will get a useful simplification of our conceptual model by noting that encryption can be used to protect data across time as well as across distance. A good example is when we encrypt data before storing it with a third-party backup service and may decrypt it later if we have to recover from a disk crash. So in this case, we need only a single encryption decryption device rather than one at each end of a communication link. This is sort of an application that, let's say, we will be modeling here. The user takes a diskette to the cipher machines, types in a key, issues an instruction, and the data gets transformed in an appropriate way. And that's how it works, to be more specific. Similar to random oracle model, we also have the random functions, that is the hash functions. So as you can see, it's quite self-explanatory. The first type of random oracle is the random function. A random function accepts an input string of any length and outputs a random string of fixed length, say n bits long. So the ELF just has a simple list of inputs and outputs which grows steadily as it works. I'll ignore any effects on the size of the scroll and assume that all queries are answered in constant time. So random functions are our model for one-way functions or cryptographic hash functions, which we may have practical uses for. They were first used in computer systems for one-way encryption of passwords in the 1960s, and as mentioned previously, they are used today in number of authentication systems. They are also used to compute message digest. Given a message, say a message M, we can pass it to pseudo-random function to give a digest, say H for M, which can stand in the message in various applications. One example is digital signature. Signature algorithms tend to be slow if the message is long. So it's usually convenient to sign a message digest rather than the message itself. Another application is timestamping. If we want evidence that we possessed, let's say, a given electronic document by a certain date, we might submit it to an online timestamping service. However, if the document is still secret, for example, an invention that we plan to patent and for which we merely want to establish a priority date, then we might not send the timestamping service the whole document but just the message digest. The output of the hash function is known as the hash value or message digest, an input corresponding to a given hash value in its pre-image. The verb to hash is used to refer the computation of hash value, and similarly the hash is also used a noun to refer to the hash value. So that's how it works in reality. And that would be it for this tutorial. For this end, in the next tutorial I'll be continuing with something called as the birthday theorem, the block, and the stream ciphers.